down. So you're given a number n, and you're asked to find, well, you're first told that that f of n is the number of integers that have common factors with n, okay? And g of n is f of n divided by n, which means it's the fraction of numbers that have common factors with n, okay? Now, anything that has a common factor with n, it means the GCD must be bigger than 1. It also means that one of the prime factors of n must be common with that number, right? So that's something we're going to use. But in reality, we needed to find this h of n, which is the number k that has the largest g value. Okay, that's really what we were needed to find. And the biggest problem was that n was just obscenely large, right? That's where the real problem was. So how do we handle this? What we said was that if 2 is a factor of n, we'll have n over 2 numbers that have 2 in common with this guy. So that's all those are going to be counted. If 3 is a factor, well, if m is a factor, then you will have n over m such numbers that will have m as common, and so they will all get counted. So all these guys will get counted based on whether they divide n. That's one. What if you have more than one factor? If 2 and 3 are both factors, then I showed you how you could count this, right? And then we kind of went to what happens if you have 2, 3, and 5, and then 2, 3, 5, and 7, and I showed you how to do this counting. I don't want to go over this again, but we did this last time. So the key observations are here. First of all, if p is a prime number, and if it's a factor of n, then you can multiply n by p. So now we have a much larger number. Let me draw this somehow. So first of all, here is n, right? We want to count how many of these numbers have factors in common with n. And then we know that g of n is f of n divided by n, which means how many of these, what fraction of these numbers have common factors. That's what we want to find out. And we want to find the number k, which has the largest g value among the numbers here, right? That's what we really want to do. And here what we're saying is, if p is a factor of integer n, then if you multiply p by n, let's say pn comes somewhere here, then you know that there are going to be p such intervals. In this interval, all these guys have something in common with n, so they also have in common with pn, right? Same thing, the exact same number shifted over here will have common things with pn. And these exact same numbers shifted over here will have common things with pn. So therefore, what we're saying is f of pn is simply p times f of n. But that's only if p is already a prime factor of n. Yeah?
You're saying that those shifting overs, they will be of size n?
They're not, yeah, right. Sorry about that. Yeah, well, if something has a common factor with n, it also has a common factor with p times n. That's pretty obvious, right? But if you shift it over here, that same thing will, because it also is a factor of n, it lands right there and then it continues again, right? So if the number is, let's say q, then what we're saying is q, let's say the common factor is, the number may not be q, but the common factor is q. That means every q thing you're going to end up at n for sure, because q is a factor of n, right? So that same thing is going to continue here, that same thing is going to continue here. So therefore, that number q is also a factor of Pn, right? So therefore, those same numbers are going to get canceled here, the same numbers are going to get canceled here. And they all will get counted. So when you're counting f of p of n, f of Pn, it's just going to get multiplied, that's all. And because there are p copies, you're going to get p times f of n. Does that make sense? So what that also means is that if I compute g of p of n, what is g of p of n? That's the fraction of these guys that have common with this. It's going to be exactly the same as g of n. Not going to be any different. So multiplying additional prime factors is not going to make any difference if p is already a factor. Now what does that mean? That means something quite useful for us because, let me see. Okay. So one of the major things you get, for instance, is let's say we try to find f of 6. 6 has, so let's say we have 6 here. 1, 2, 3, 4, 5, 6. So that's 6. Clearly 2 is a factor of 6. So is 3. 3 times 2 is 6, right? So therefore, 2 and 3 have common things with 6, but so does 4. Why? Because 4 has 2 as a factor, and so does 6. So therefore, we're going to cross out, we ignore 1, nobody cares. We're going to take 2, 3, and 4 as things that have common factors with 6. 5 does not. So therefore, g of 6 is going to be 3 divided by 6, right? Because there are 3 numbers that have common factors with 6, and the denominator is 6. Yeah? So therefore, what we're saying is, if I go to 12 now, the exact same numbers shifted over here are going to have common factors with 12. All right, so for instance, so we did 2, 4, 6. We're going to do 8, 10, and 12. All these are going to, by the way, 6 also should have been counted, so this should have been 4 divided by 6. Sorry about that. So if I take multiples of 2, I'll get 2, 4, 6, 8, 10, 12. The same things over here got marked over here. If I take multiples of 3, I'll get 3, 6, 9, and 12. Exact same things got marked out. And you see that both intervals look exactly the same, right? You had 3 things marked in between here, 3 things marked in between here, and then this guy and this guy were marked. So it just gets repeated. So I can take 24, I can take 48, doesn't matter. I'll get the same density as I increase it. Yeah?
Your P here is 2?
P here is 2.
Yeah.
I could do this with 3,
Yeah.
right?
Okay.
So as long as I keep multiplying by something that's already a factor, nothing changes. And that's important, okay? So therefore, I only have to look at the prime factors once. I don't really care. So therefore, the g value for 6 is going to be the same as 12, is going to be same as 48, same as 96. Okay? because there only 2 and 3 are factors there. Is that clear? So this is going to be important, and so all we care about is what are the prime factors. And we only care about it once, because you multiply it more times, it won't make any difference to the G value. All right? So we're going to use that fact and say that G of n, let's say is P1, if its prime factors are P1 through Pk, it doesn't matter how many times P1 appears or P2 appears. I only care about it appearing once. I'll just use that to figure things out. Okay? And then other interesting things happen. G of 2, so let's take 2. We know that in G of 2 it's going to be 1 divided by 2, right? G of 2 must be less than G of 2 times 3, because now we have 2 prime factors. 2 is already going to cross off every alternate one, but 3 will knock off a little more. So if you have 2 and 3, it's going to be better than just 2. If you add 5 to it, it's going to knock off even a few more. You have 7, it's going to knock off a few more. So your density will increase. The fraction will increase. Are you with me so far? Did I lose some of you? Ask away, or else it's just, train is just going to keep leaving. Yeah? Questions?
I came a little late, so I don't want to.
It's okay. It's all right. Ask a question. Slow me down.
I kind of missed out on the point you were making because I get that because 2, 3.
You get that it'll be, yeah.
4 have common factors with 6. If we shift it by 6, it becomes the same common factors with
Right.
12. But like, is that the only point you were trying to make?
So because of that, the density, this fraction of numbers that have common things will also remain the same.
Will be the same for 6 and 12.
Yeah. Does that make sense?
Yeah, that makes sense.
Okay. So what that means is that if you look at 6, what are the prime factors? 2 and 3. If you look at 12, what are the prime factors? Again, it's just 2 and 3. It's just that 2 appears twice. As long as it's just 2 and 3, you're going to get the same G value. That's the lesson. Right. So I could go up to 48. There'll be lots of 2s and lots of 3s, but it's still going to be the same. Okay? All right. So, but then if you add additional prime numbers, it'll add a little more. Okay, so what have we learned? We've learned some interesting things. We know that G of 2 is less than G of 2 times 3 because you're adding a prime number. It's less than, so as you add more prime numbers, you're going to get better. Here's another one that's very useful. If I take 2, 3, and 5, sorry, before that I should say that G of 2 is better than G of 3, is better than G of 5. Why is that? Here you're going to knock off every second one, right? Correct? Because every second number, every even number, will have 2 as a common factor. And so therefore you're going to get, well, we know that G of 2 is half. So that means any even number will knock off at least half the things. Every number that's a multiple of 3 will only knock off every third item. So at best, this is going to be 1 over 3. This is going to be 1 over 5, and so on. Nothing else gets knocked out. Right? Is that clear? Which also means that if it's not just 2, if it's 2 squared, or if it's 2 to the power 20, you're going to get the same fraction. It's going to be a half. Same thing over here, same thing over here. So this is the order in which the fractions go. Here's the key one. This says if you have 2, 3, and 5 as your factors, that's going to give you a better G value than 2, 3, and 7. Why is that? Well, 5 is smaller than 7, which means it's going to knock out a few extra items than 7. In fact, 5 knocks out only 1/5. 7 will knock out 1/7. So if you replace 5 by 7, you're only going to end up knocking off less number of things. And so therefore, this guy's G value is going to be larger. Is that clear? Well, I can actually go a little higher and say 2, 3, 5, and 7, or 2, 3, 5, and 11. Which one's better? This guy is going to be better, right? That's obvious. So what this means is, if I have k distinct prime factors for two different numbers, let's say I take two numbers, n1 and n2. This has k factors, and this also has k factors. But one of them is slightly smaller primes than the other, then the first one's going to be better than the other in terms of its G value. So if P1 is smaller than P2, then G of P1 is bigger than G of P2. And when I combine things, I'm going to have slightly better if I use P1 instead of P2. So it turns out that this is just enough to kind of figure things out. I'll show you some examples. Let's say n is equal to 15. Well, let's look at all the numbers between 1 and 15. G of 2 we know is bigger than G of 3, bigger than G of 5, bigger than 7, bigger than 11 and 13. These are your prime numbers. So I don't have to consider anything other than G2 because that's the biggest so far, right? But G of 2 is the same as G of 4, is the same as G of 8 because all factors are just 2. And this is actually better than G of 3, which is same as G of 9 because that's just a power of 3. So far, G of 2 is the best, right? But then G of 2 is not as good as, say, 2 times 7. So 14 will have a better G value than 2. Okay? 14 will not only knock out all the even numbers, but it'll knock out a few extra ones that are multiples of 7. But then 2 times 7 is not going to be as good as 2 times 5 because I'm using a smaller prime number. That's not going to be as good as 2 times 3, which you use an even smaller number. So therefore, 2 times 3 is so far the best. But 2 times 3 is the same as, if I can go and add an extra 2. So 6 is same as 12 in terms of its G value. And we also know that it's better than 3 times 5, which gives you 15. So if you look at all these relationships, we've taken care of all numbers, and we've convinced ourselves that 6 is the best. Is that clear? Wow, you guys are not too happy today. What's going on? I'll switch to a different problem if you really don't like this. So, are you okay with this example? Can I move on? Yes? No?
Okay, yeah.
All right. Grudgingly, he says yes. Say n is equal to 150. Now let's solve the problem. Again, 2 is the best. I don't have to look at other prime numbers. 2 times 3 is the best because those are your first two smallest primes. So 6 is good. But if I add 5 to it, so that's 2, 3, and 5, that's going to be even better. That's 30. Now can I take 2, 3, 5, and 7? That'll go out of range for 150. So this is your best. So your answer is 30. Done. So go and figure out what the G value is for 30, and you would have the answer. Is that clear? So if I want even larger, this is what I do. I keep multiplying the next prime until I exceed the number, and then whatever is that number I get, that's my best answer. Now go and figure out the G value. And to figure out the G value, we discussed last time, go and check the video, and you'll know exactly how to do this. Is that clear? This is not easy, but hey, I thought it was fun. maybe, right? A lot of fun, right? So, yeah, I think you can read this. Here's the algorithm, if you want, right? It says, first thing you have to do is to compute the prime numbers. If you don't know the prime numbers, well, you have to kind of figure this out. And there are several algorithms. They're there in any textbook. You can go code this up and write it. So you generate the list of primes, and then put them in an array, and then start with the smallest primes, keep multiplying them until it crosses n. Wherever it crosses those primes there, multiply them, and whatever number that gives you, that's going to give you the best g value. And then in order to figure out the g value, I told you an algorithm last time, go and use that. That's your stuff. That's the whole thing. Is that clear? Okay, let's move on to something else, something more fun. Are you ready to talk about swords? Who has not heard of the sword counting problem? You have not heard of it. Okay, too bad. All right, let's go over this. So here's what the problem is about. It says you're given a graph, and you're asked to count how many swords there are in this graph. What in the world is that? A sword looks like this. Okay? It's got 6 vertices, and you're given some complicated graph, and you're supposed to find as many of these swords as possible. And you're supposed to count these and give them the answer.
6? Not
Sorry?
7?
What's
Like,
that?
would it be like a long sword?
No, it cannot be longer than this. That's it. It has only 6, fortunately. Right? So yeah, you don't have to be King Arthur or anything like this. It's just counting.
Wait, how many, like, all the edges are swords?
No, this whole thing is a sword.
Or is just one sword?
Yeah. So for instance, let's say my graph looks like this. Let's say this is my graph. And I ask you how many swords there are. And what's going to be your answer? Sorry?
0.
I have no idea. Actually, it is 0. You're right. So that's not very good. Let me add some more. Okay. Maybe I should make them as letters instead of numbers. And let's take out one of the edges here. Okay? Does this look easier now? So I'll show you one sword. Here's one sword. I can take that, and that. That's a sword. You see a sword there? You get it?
So it's a sword because it has what? Because it has 6.
Because this B is the same as this D, and then it should have 3 of these guys, and then it should have a path of length 2. That's boom, that one.
So it needs one vertex to have it in degree of 4.
Well, degree of 4. There's no in or out.
It's undirected.
It's undirected.
Well, to be connected to 4.
Yeah, it has to be connected to 4. That's correct. Degree of 4.
Are only connected to 1.
And well, there's B that's connected to
Yeah, to
2, and the rest are connected to 1.
4 to 1 over.
Yeah, well, you know, in the graph, these guys may have higher degree, which is okay,
Right.
right?
Yeah.
Yeah. So this is one sword. Can you name another one? You could easily just flip this, right? But can you tell me something that where you don't flip it? Or is that it? Maybe that's it. Looks like, no, there are more. There's obviously 2, right? Which one is this guy and the other is a mirror image of this. Can you tell me one more? Yeah?
Instead of E to D, we can do go from C to D.
Right. So let me use a different color and convince the naysayer. So what were you going to say?
Instead of E to D, we do C to D.
Right. So take this out and add this, right?
Yeah.
Is that clear? So there are a lot of swords hidden here.
There's 4 swords.
There are 4, no, there are more.
Well, for that one, there were 2.
There's way more.
There's one starting from F.
Sorry?
There's one starting from F as well.
Yeah, well, I could go, let me use one more color. I could go like this,
But
and,
we can't.
oh, I can't go here, you're right. You are right. All right, maybe that's it, yeah. Okay, 4. Okay, thank you.
Can't you have one from F and A, and then also from F, an H from F and A, and H from F and E?
Well, there are mirror images of whatever I just showed you, the green and the red, yeah. So that's how you get 4. So if I give you a larger, messier graph, this could be a real pain, trying to count the number of swords. So the rules say that 2 swords are different if the set of edges are different. So here, the 2 swords that I showed you in green and red, they had the same vertices, but the edges were different, right? Yes? So the main constraint you have to deal with is that you could have up to 100,000 vertices. Real pain in the butt. So if you're not careful, things can get very hairy with a 100,000 vertex graph. And you're supposed to count these things. Fortunately, there's another thing that's going to save you, and that is it says that there are at most 100,000 edges. And you'll see later why this is going to save you. Any questions so far? Everyone clear about what a sword is and how they look in a graph? Yes? Okay.
Actually, maybe if we could go over that one more time. So a sword. So I guess we need one with, like he said, like degree of 4.
Yes. So the degree of 4 is here, right?
I guess because it's okay. Oh, okay, I see it. I guess it's those that you put in red.
So these are the red. So if you follow the red, 1, 2, 3, 4, but then one of them has to have a path of length 2.
Of length 2. 2, you said?
Yeah, draw it. Use some paper. Go for it. Scribble something. It's good for you. Okay. So as I said, the rules say that 2 swords are different if the set of edges are different. It doesn't matter if the vertices are the same or not, but the edges need to be different. Okay? All right.
You're like drawing.
Yeah, we're going to watch you. No, go ahead. All right. So we're going to try and interpret this. What does it mean to say set of edges are different? Well, it turns out there are 2 possibilities. One is the set of vertices themselves are different. If the set of vertices are different, for sure the edges are going to be different. But it's also possible that the vertex set is the same for the sword, but some edge there is different. Okay? So we need to understand this a little bit better. So here's the deal. If your vertex of degree 4 is different in the two swords, then they are not going to be the same, right? So in one case, B was your degree 4 vertex. In the other case, it was F. These two swords are never going to be the same. So the vertex with degree 4, first of all, will tell you that these are two different swords or not. Next, the vertex of degree 2, if it is different, if the degree 4 vertex is the same but the degree 2 vertex is different, then again, it's possible that you're going to get two different swords, right? And finally, that guy there, the tip of the sword, if it's different, then again you're going to get a different vertex, right? The different sword. And the last but not the least, these three guys, if you change any of them, you will get a different sword, but if you just flip them around, it's not going to change the sword. Are you clear? So even if you switch these around, the edge is still going to be DF, DC, and DE. It's just that the order is a little wacky, right? Yeah.
Can you clarify where it says A cannot be switched?
A cannot be switched with anything here. If you switch A, if you switch the tip of the sword with anything, you're going to get a different sword.
Okay.
That's all I'm saying. If you switch the degree 4 vertex with anything, you're going to get a different sword. If you switch the degree 2 vertex with anything, you're going to get a different sword. Here, the only thing is that if you just switch them between themselves, it's not going to change the sword. Right? Of course, if you switch these with A, B, or D, you'll get a different sword, no question. But if it's only exchanged between themselves, they're totally identical, and the sword doesn't change. So you shouldn't be counting different swords for just relabeling C, E, or F. Okay? Is that clear? All right. So that's just to get things clear in our head. What is a sword and how you count them? Because otherwise, we'll just end up counting things more than once. Okay, so here's a first draft of the algorithm. And maybe even before I show this, why don't I ask you for one? What's the silliest, most ridiculous way you would solve the problem? Yeah? Yes?
Visit every vertex and see if you can construct a sword from that vertex.
Okay. It's not detailed enough, but good. So here's how I would do it. I would try every possible choice for the degree 4 vertex, every possible next choice for the degree 2 vertex, every possible choice for the tip of the sword, and then I'll pick 3 other vertices from whatever is remaining, and I will check if these 6 vertices form a sword. Okay? If they do, I'll count it. If they do, I'll just keep some counter. Cool? This is the kind of silly algorithm you need to write down first for any of these weird search problems. That'll help you. Okay? This is ridiculous. Why?
The input size too big.
The input size is too big. You have 100,000 vertices.
Yeah.
That's crazy, right? So it's going to drive you nuts because this is roughly n times n times n times n cubed. That's n to the 6th. With 100,000 vertices, it's not going to happen in our lifetime, right? So, okay, this was a good first draft. Let's figure out how to improve this. Are you with me? Everyone okay with this? Okay, good. Next, I am going to make a second draft where the first thing I did was, instead of picking the vertex of degree 4 to be any of the possible n vertices, I'm just only going to pick the ones that have degree 4 at least. right? I could have added degree 2 for B. I forgot. That's fine. But I've done something more. I have, for B, I'm not picking any vertex in the graph. I'm only picking things that are adjacent to that guy. That at least narrows down the field a little bit. May not be a whole lot, right? And then for A, I'm not going to any vertex. I'm only picking things that are adjacent to B. And then for the other three, I'm only going to pick things that are neighbors of D. Is that clear? So among these choices, I am going to check if they form a sword, and if they do, I'll count it. Well, actually, I can do something slightly better. And what is it that I can do better? Any thoughts on this? Instead of checking whether these 6 vertices form a sword, what can I do?
Not sure though, but like maybe some variation in the minimum span tree.
Okay, that's a thought.
Wouldn't it already be a sword if all those conditions are met?
That's right, because those conditions already verified that they are swords because B is adjacent to D, right? That took care of this edge. A is adjacent to B, that took care of that edge. And these 3 are adjacent to D, so it's already a sword. What more is there to check? Right? You believe that? That's a sword. So I don't have to check anything, and I can simply say count. Right? A little bit of work saved, not a whole lot.
So now it's n to the 4.
No, it's still n to the 6th. Well, no, you're right. It is a little bit better. It's maybe n to the 5th. But the problem is it's not so clear how to count this. And I won't get into the details. Let's just say that we've improved it a little bit, but in reality, not a whole lot. What should I do to improve this further? Any thoughts?
Well, okay, first of all, what do you mean it's not very clear? I guess the algorithm is not very clear how it works.
No, the time complexity is not clear.
Oh, okay.
Yeah, but that's okay. We won't dig into that for now. Yeah,
Okay, there's not like a full-fledged idea, it's just like a suggestion.
That's
right?
fine.
Maybe you could like pre-compute some of the things. Some of the
Pre-compute.
things on the graph.
okay, pre-compute is good. So pre-compute what? So it turns out that I could pre-compute degrees. All right, but those are all going to be, you're going to squeeze out a little bit of speed there, not a whole lot. Any other thoughts? Yeah.
For the last part, if we know how many neighbors there are for D,
Yeah.
we can do like an n choose 3 to find the
So
count.
instead of trying every possible triple of neighbors, if this vertex D has 7 neighbors, I don't care which 3 I pick, it's going to work out for me, right? So why don't I just count? And how do I count? It's exactly what he just said. Instead of doing this combination, I'll just look at the degree of D and see how I can pick 3 vertices from that set. In the previous draft, we went and looked at 3 distinct neighbors of D to figure out these 3 guys. What I'm saying is, if D has this many neighbors, then all I have to do is to pick 3 out of them. Actually, I did something wrong. I should have said degree D minus 1 because I shouldn't be including B here, which has already been picked. So I'm sorry. This should have been degree D minus 1. Out of degree D minus 1, I only have to choose 3, and I know how many that's going to be because if D had 7 neighbors, B is taken care of. There are 6 others. I just have to pick 3 from there. So it's 6 choose 3. All of them are going to work out because they're all neighbors of D, right? So it doesn't matter which 3 I pick here. it's just going to give me different combinations. I might as well directly count them instead of listing them out and then counting one by one, which is ridiculous. Okay, so we improved that. That's great. That means some n cubed has just disappeared, boom, right? So maybe we're somewhere close to n squared. That's still nasty because n is 10 to the 5, 100,000. N squared is still 10 to the 10. That's not going to bode well for you.
Like 10 billion.
Yeah, that's not good, right? So we have to squeeze out a little bit more. Yeah.
Okay, just to clarify, like, yeah, I'm not quite sure if I completely follow. So degree D, choose 3. So I guess what we're doing is.
Yeah. So okay, right. Okay, let's do a simple picture here. All right. So here's my graph, which looks like a big egg.
Okay.
Somewhere here, I picked my vertex D.
Okay.
That's my degree 4 vertex.
Okay.
Okay. Then of the remaining, of the ones that D is adjacent to, I said, okay, I'm going to make that my B. Of course, there are many choices, but I picked B.
Okay. Okay.
Then I said, oh yeah, let me pick one of its neighbors as A. Of course, it has many neighbors.
Oh, okay. Yeah. Okay.
Yeah, that's my next for loop.
Okay.
And then I have to pick 3 that are neighbors of D.
Hmm.
How many ways can I do that? Well, D has degree that. Degree of D.
Okay, I see why it's D choose 3 now. Okay.
So from this, I have to pick 3, but I can't pick B, so I should really make this degree D minus 1, choose 3.
Oh, okay.
Is that clear now?
Yeah.
Okay. So that's how I got this count, and I keep adding them to my count. Good? What else can I improve?
There might be some test cases you have to watch out for, but instead of iterating for A adjacent to B, you can just look at the neighbors of B minus 1.
Yeah. Where? Sorry, I'm not quite following you. Say that again.
Let's say B had another edge that goes to L and G.
Yeah.
Instead of iterating over
So
everything,
yeah, I know B has many vertices,
Yeah.
neighbors. Yeah.
So the neighbors of B minus 1, that's some of the different tips you can have for this work.
Right. So there are a few corrections I still have to make. This is still not the final draft, so bear with me. But yeah, essentially, regardless of whether I make this as my A vertex or this as my A vertex or this as my tip of the sword, they're all going to work out the same. So therefore, what I'm doing here is simply going to remove one of the for loops and squeeze out a little more. So here's how that goes. I got rid of that for loop, which is what you're suggesting. And I am now going to make this that multiplied by that. Okay, is that clear? Why? This was there before. For each choice of those 3 vertices at the handle of the sword, this was number of ways I can pick the tip of the sword. Is that clear?
What if B is
Yeah.
connected to?
Yeah. yes, absolutely right. That's what I meant by it's still work in progress here. Nobody said this is final. You're absolutely right. So there's some work. But are you getting this? Okay, now this is close to being the final, except for the problem that Ricky just mentioned. And what was that? Did anyone catch it? So it's possible that the neighbor that you picked, A, is actually one of the neighbors of D. Right? If it is, then, oh yeah, then you have to make sure that you don't pick that guy as one of your choices. So it's a little annoying, and so you have to account for it. And I haven't done that correction here. I'm going to let you figure that out.
so I have an idea,
Uh-huh.
but I don't know if it's possible.
Yeah.
But if we're able to count all cycles of 3,
Yeah.
then we're able to
Uh,
find this number.
Well, all cycles of 3 will kill you because that's already at least n squared,
That-
maybe
that's
even
what I
worse.
meant. Was
So
that
that's not going to work out. Instead, what you have to do is the following. You have to look at the, and in fact, so some of the implementation, let me talk about that in a minute, and this would start to make sense. Okay? It does make things a little messier, but this basic idea, if you've understood, then you're there 90% of the way. Okay? So now it's just fine tuning it. Now it's saying, did I screw up somewhere? For instance, if B is adjacent to something that D is already adjacent to, what if I take that as my A? Then my choices for the neighbors of D goes down, and so I have to worry about this, right? So when I pick A, I have to, anyway, it's not just degree B minus 1, but I have to, if I pick that, then the number of choices here changes. It's a real mess, right? So I have to account for that slightly separately, but let me give you some ideas. I'm not going to give you all the details because I didn't work all that out and put it here, but it's possible, all right? What is important to note here is that you're now going from n squared to something like order of m, which is extremely important because you're starting with every vertex. It's true that you're trying every vertex, but then you're looking at every neighbor of the first vertex, and so you're essentially looking at every edge, and that's what your time complexity is going to be. And in order to pre-compute the degrees, again, that can be done in big O of m time. And fortunately, you're told that the number of edges is also at most 100,000. And that's why I was saying that's a critical constraint. Without that, you're dead meat. It's going to take way too long. Okay? Yeah.
For that problem we were talking about, that's only the scenario if D has exactly degree of 4. Because if it has degree 5, then we
No,
put-
but even then, you have to then reduce this even further. The choices goes down.
Wait, what?
Yep. So here we said for every choice of A, that's this many,
Yeah.
you have this many choices for C, E, and F. But those choices goes down. Because now one more of the neighbors of D got knocked out. Right? Let me draw a picture.
Yeah.
Here's the vertex that I picked for D. I have many choices for B. I picked one. I made this guy B. Then I have many choices for A, and one of those is a neighbor of D.
Oh, I see what you mean. Okay, yeah.
So if you pick that as your A, then the choices for this has gone down even further. Earlier, you only give, it goes, since there was 6 here, 6 minus 1, 5, 5 choose 3, now it's going to be 4 choose 3.
Yeah.
From that A would become the B, and then that B would become the, and that's like a repeated.
It's a little bit annoying, yeah.
That would be repeated.
Yeah, it's the same source.
Right, it's different structure. It goes
No,
through a
no,
different.
okay, yeah, but the B goes to that B, but then it goes to that A as the B, and then goes to B where it's A, and that's pretty much the same source.
No, so what you're saying is that when you count it with A as the B and B as the A, you'll have the same problem. That's what you're saying, right? So actually, you're absolutely right. So you could figure out how many common neighbors D has with B, and simply use that to improve your. There should be a simple formula fix, but I haven't thought this through.
But I think he's also saying that if the blade, let's consider the blade is DBA, right?
Yeah,
I think he's also saying that the blade DBA and DAB
yeah.
are the same.
No,
That's
no,
it?
it cannot be the same. They are two different swords.
Yeah.
But like,
No, no, but what he's saying is that when you, if you were to do this problem where this becomes the blade and this becomes the tip, you would have the same problem again.
Okay, yeah, then this.
Okay. So, roughly this is what we said. There are some implementation details. Oops, what happened to my slide? I'm missing some things. One thing that's very, very important is you cannot store the graph as an adjacency matrix. You have to store it as an adjacency list. Otherwise, your time complexity blows up. You can pre-compute all the vertex degrees. If it's an adjacency list, you can do that in big O of m time. Why? Because remember, adjacency list says for each vertex it has all the neighbors. You just have to count the length of that list. That's your degree. It's relatively easy to do. But it's even more important because then you have to find the common things between you. Not only do you have to compute the degree, but you also have to compute the common neighbors of two adjacent vertices, which is what he called as triangles. And that you have to be a bit careful about, but it can be done. And so the way you do that is by doing set arithmetic. And so you use a bit array to keep the neighbors of A, another bit array to keep the neighbors of B, and then simply do a intersection. So that would be an AND. And so you can quickly figure out how many things are neighbors rather than going through the list. And if you have that number, then there should be a simpler fix. I'll see if I can figure that out later today, and maybe I'll email it to you guys. Okay. But at least do you now have the handle on this, or was this triangle problem the only problem you had?
That was the main problem, the last problem.
Yeah. Okay. So that's actually not solved then. All right. Well, we'll figure this out. How am I doing on time? Good. I have 20 minutes. So are you ready for the next problem? Yes? Yeah, we're going to do the Venn intervals. Anybody looked at this? And what's the verdict? Yeah. All right. Anyone wants to describe the problem? It's kind of complicated. Want to give it a shot? Have you seen this problem before?
I'm sorry, but I didn't read through it. I think it was part of the qualifier question.
Yeah, all these are from NAQ.
Yeah. Yeah, you want to give it a shot?
Oh, I do not remember.
Yeah?
I'm
You try.
reading it right now.
You read? Okay, fine. David, did you look at this? Or should I just go and explain it myself? Okay.
Yeah. Oh.
You have
yeah,
to
I
go?
have to go a little early today, so.
No problem.
Yeah.
Take
Bye.
care, bye.
See you guys.
Have a good day.
You too.
All right, so this problem says you're given something called a list of regions, and you're supposed to output something called a non-degenerate Venn interval diagram. All right, that's a really bad start for defining the problem, but we need to dig into it before we understand this, okay? Now, what the heck is a region, and what the heck is non-degenerate, and what's a Venn interval diagram? That's what we need to figure out. So your input, at least the no. So that's what the problem is. The situation looks something like this. Here are some intervals. Okay. Each of these intervals, you should think of this as a set. It's a set of values between -1 and +1. This is a set of values between 0 and 4. This is a set of values between 2 and 5. This is a set of values between 3 and 6. This is between 7 and 8. F is between 8 and 9. Those are all sets. And when you put them on a line and look at all the intersections, it all breaks down into smaller things called regions. And each region can be described by what set contains that particular region. So here only values from B are present. Here it's both A and B, right? Here it's only A, here it's A and C, here it's A, C and D, here it's C and D, here it's only D, here it's nothing, here it's E, and here it's F. All right? Now, you can get this quite easily from if you're given this. Because all I have to do is mark all these endpoints, right? And then figure out what things are intersected, what things cross this region, right? So these are called regions. Those are called sets. Are you with me so far? Sets, regions. If I'm given sets, I can figure out the regions quite easily, right? But now the problem is you're given this instead of that, and you're supposed to figure that out. So you're given the regions, and you're asked to figure out the sets. Did I say something obscene, bad? What happened? That's clear? So the thing is that you just need to figure out, relatively speaking, how these sets sit on the interval, sit on the line. Yeah.
But you figure out like different intervals of the sets, like not like actual values.
Yeah, the actual values don't really matter. What really matters is what starts after what ends after what, things like that. Which ones intersect. Okay. So it's really the order of start points, left endpoints and right endpoints that you want. If this end of B moves a little bit, it's not going to change the regions per se. It might change the region boundary, but it's not going to change the order of the regions that you get, right? So if I gave you the regions, can you figure out the actual sets? Now, if I gave you these intervals in this order, if I told you that B came before A intersect B, before A intersect C, and so on, then it's easy. Why? Because this has A, this has A, this has A, this has A, so A must go from here to here, right? This has C, this has C, this has C, so C must be here. Pretty obvious. The problem is that in your input, you're not given the regions in any order. Okay?
Parts of the region.
No, you're given all the regions.
No, but you're given it in blocks, like.
You're given in whatever order they like.
Yeah.
It could be in absolutely any order that they want. All right, so here are some definitions that we already talked about. A set is one of these intervals, right? And it's written in this strange notation because it includes the left endpoint, but it doesn't include the right endpoint. That's okay, minor detail. And a region is the stuff on the line here. So it's these intersections that you get. So this region tells you that this is an intersection of A and B. That doesn't mean it's the entire intersection of A and B. It just says that here only A and B cross this portion. That's all it's saying. Now, so here you have 6 sets, and you have all those intersection regions. One good thing that you're told is that none of the regions repeat themselves. Meaning, if I see an A intersect C here, you're not going to see it again. You're not going to see A intersect C one more time later on. That's not going to happen. So it appears only once. One more thing that you're told is this thing about degenerate and non-degenerate. So let me go back to this definition here. Remember, we were asked non-degenerate Venn diagrams. A Venn diagram is non-degenerate if one is not contained in the other. So you cannot have C ending right there. If it ended right there, it would be completely contained inside A. That's not allowed. Okay? So our job is to figure out a layout of the intervals that are non-degenerate. Okay? Which actually makes life easier for one not to be completely contained in the other. Okay? Go for it.
I don't want to, maybe like a hash map, and then it would be like the name is, the key is the region name, and then beginning and end. But we also need maybe a map.
You don't know the order. So that's why, again, it's useful to think in terms of a naive algorithm. What's a naive algorithm here? So a naive algorithm says, here are my regions. I'm going to try every possible permutation of these regions and check if it forms something valid. Because all the A's should be together, all the B's should be together, right? That's a valid order. Any ordering of the intervals will make sure that anything that has A in it is all together, right? Because this is where A starts, this is where A ends, so everything, all the regions must have A in it. Is that clear? So if I can order these in a way that rule is satisfied, then I will have the right answer. The only problem is that there are n factorial. If there are n regions, there are going to be n factorial such permutations. So that's your naive, that's your brute force algorithm. Now we're going to see how to make this a little bit better. Questions? What are the constraints here? I think I forgot to write that down. Can you tell me what the constraint is for the number of regions?
N is 4,000.
4, okay.
K is 2,000.
Okay, so it's somewhere in the thousands. All right? If it's 1,000, immediately you should know that n squared is okay, but n cubed is not. Okay? These are things that should just go in your head. So it's okay to look for n squared type algorithms. Do not even entertain n cubed algorithms. And forget about n factorial algorithms. You can't try all possible permutations. Is that clear? Yes?
Just something that I've noticed and I want to see correct. For any two, so let's say we're doing a two for loops, one nested within the other.
Yeah.
We look at all the other ones. If the start is contained within another interval or the end is contained within the other interval, we have to make sure that either the start is unique or the end is unique. Like one starts earlier than the other one starts later.
Tell me in terms of the example. What are you trying to say?
So let's look at B.
Yeah.
Let's iterate over all the other intervals.
Yeah.
First we see that D and B do not intersect, so we can just continue. There's no issue there.
Yeah.
And now we go to A. We see that D and A do intersect. So now we want to look at either both of their starts or both of their ends. To see
Yeah.
if one starts earlier or one ends later. To make sure that there is no
Sure,
overlap.
that's a good idea. that would require you to look at n squared pairs, right? And it'll get you some pairwise information.
Yeah.
So it does turn out that that will become useful, and we'll see how to exploit that idea. Other thoughts? Okay. So as I said before, the easy problem is if I'm given the sets, meaning the intervals, I can find the regions. If I'm given this, I can find this. All right, that's easy because all I have to do is to sort the endpoints and then map it down and then figure out what intersects what, right? So the hard part is the other way around. So this tells you how you're going to do the easy problem. Just to get this in your head, because they also explain that in the problem, and that's reading all that is going to be is sometimes the challenge, but it's there. So the real problem that we need to solve is the inverse of this problem, which says I'm not given the original sets, I'm given the regions, I'm given this part, and I have to figure this part. Okay, so I'm given these guys, and I have to output the left and right endpoints of these sets. And the big challenge is that the regions are not given to you in a nice order. If they were given to you in the nice order, it's trivial. Okay, all you have to do is to check whether this ordering is okay or not. So checking whether this order is good or not is somewhat easy, because you can look and see that B, it's together here, A is together here, C is together here, D is together here, then you have E and F. So everything is together, and so you're going to be in good shape. You can figure out a start and end point. Is that clear? All right. So any thoughts now? Any new ideas based on what we've seen? So the first thing you're told is that no two regions are the same, meaning no two regions are the intersections of the same collection of sets. Right? Here's another important property, and that is that adjacent regions cannot add or subtract more than one set. So you can't have over here a region that has A, and then the next region to be A and A intersect C intersect D. That's not going to happen. Why is that?
Does it mean there was like two regions would start and end at the same point?
Yeah, what's wrong with that?
Enclosing?
Sorry?
They would like enclose?
It doesn't immediately enclose, but if both start at the same point, one of them must end earlier, then they would become, one becomes contained in the other. Okay? So if two things end or start at the same point, you would have this problem, and that's not allowed. Okay? So for our good and valid solutions, we know that we don't have to worry about this. And in fact, you can check over here. You can see that here it increases by 1, decreases by 1, increases by 1, increases, increases, decreases, decreases, increases. And here, it's a nasty case where it's decreasing and increasing. Okay? So that brings us to the other possibility that you could have adjacent regions that differ by more than one set, but then one has to be an addition and the other a subtraction. That's what's happening here. Is that clear? We're going to deal with that case separately. This is an annoying case. So for now, I'm going to ignore it, and we'll worry about this at the end. Okay? Let's see what happens if this case doesn't happen. Oh, I forgot to animate this. I'm so sorry. So our goal is going to be to model it as a graph problem. You already saw that, which is similar to the idea that you had a few minutes ago. How do I make this a graph problem? What are my vertices and what are my edges? So vertices are?
Let's like first where we have E by itself.
Are vertices these guys or these guys?
Oh. At the bottom there?
This is what's input to you, so that it better be this,
Yeah.
right? So inputs, my inputs are these. I make them my vertices. Each one's going to be a vertex. I just don't know the order. But then I need to decide what the edges are going to represent. And you said that
The intersection.
the intersections between,
Two sets. Like,
no. That intersection already determined this. So you're already told that this is A intersect B. All right? So you're given all these names, but you're not told in what order they show up. Okay? So for instance, you might be given in the following order. Say you're given A first, A intersect B next, then B, then A intersect C, and then A intersect C intersect D, and so on. So if I just switch these two and gave it to you, you're going to run into a problem.
wait, what?
Because now B is contiguous, but A skips here and then continues again. That's not going to work out for you. Does that make sense? Yeah.
So the vertices are like the actual thing that's given, like A intersect B.
Right.
intersect
Those
B.
are, they're called the regions, yeah?
So the actual regions are the vertices, right?
Right.
And what we want to get is like some sort of an order. What if we connect like every B to every other region that B appears and every B to every
Okay.
other region that
So therefore, our edges represent intersections between sets.
Yes.
Okay? So that's what we're going to try and do. So we represent each region by a vertex. That's these guys. So you're going to have a vertex for each of these. We're going to throw an edge if you have if they have something in common. First, before we even think about that, let's think about what will happen here in this example. If I don't know anything about the order, and if I represent each of these with a vertex, what do you expect? You would expect that these two are connected by an edge because they have B in common, right? You would expect these two to have an edge because they have A in common. These two have A in common, A and C in common, C in common, D in common. So all the neighbors have something in common until you get to here where things kind of go off to a blank, and then there's no intersections here. How does that help you? Well, so remember, we are not going to think about this case. We're only going to think about this case here because here weird things are happening. Let's focus on this easy part first. So what we're saying is, as long as it differs only by one set, meaning either you add a set or you remove a set, which means either a new interval starts or it ends. So either it's one of these start points or it's one of these end points. If something starts, then it gets added over here. A gets added here. If something ends, B goes away, right? So here you're adding something, here you're subtracting a set, right? So as you go along, as long as it's this good case, you'll see that every time a set either gets added or deleted. Except when you hit a gap, then you start afresh again. So when you think of this graph, what does this graph look like, and how does that help you? That's the question. Does that make sense? Does the question make sense? So what do you think? By the way, I changed something here. You said earlier that I'll throw an edge as long as there's an intersection. Here I'm saying add an edge only if the region differs by one set. So I'm making it a little more restrictive. So therefore, I won't have an edge from here to here. I won't have an edge from here to here because they differ by more than one. Okay, but I'll have an edge between these two. I'll have an edge between these two. Does that make sense? So I've restricted the kinds of edges I'm adding. Yeah, you have a thought on this?
I was going to say, well, they have to differ by one when we're looking at edges.
Yeah.
But if we're adding one, it should be from the one that has one less to the one that has another one. So from like B to A intersection B, there should be a directed edge. And then from A intersection B to A, there should be one from that to that.
Sure, but remember there's no ordering. So these are vertices. The vertices are just sitting like so. I have no idea what goes where. So this is A intersect B, this is A intersect C, this is A intersect B intersect C, things like that. And I have no idea in what order. I can't, because I can't place them on the line yet. My question is, if I apply this rule, what is this picture going to look like? Yeah.
I was just going to ask what that question was.
Yeah.
So you're trying to figure out a way to construct this graph based on the
No, my graph is easy. I've told you exactly how I'm going to do it. My input are these sets, right?
Yes,
It's just that they're not in any order, right? So I make a vertex for each of these guys.
yes.
Then I'm also telling you how my edges are going to look. They are going to connect two things if they differ by one set, meaning either you add a set or you remove a set. That's all.
Oh, okay, I see.
Okay.
I was just thinking.
Yeah.
Previously you said that for every region, its neighbors is either adding or removing one?
Yeah.
So what
That's
would-
why I made the edges like that. That's right.
So would it look like just one big circle, one big cycle?
Well, that's what I'm asking. What does this graph look like? Are you sure it's a cycle?
Just one path. Like
He thinks it's only a path.
Oh, no, you're definitely right. It's
One
that.
edge.
That's definitely
a
right.
cycle minus one edge.
Yeah,
Yes.
it's that. I've seen it.
That's right. So does this make sense?
Yeah.
Well, I'm still thinking about it.
You're still thinking about it. All right. So let's ask this question. Can a vertex have more than two neighbors? So let's say this is A. Can this be A intersect B, A intersect C, A intersect D? Is this possible? Forget about that picture there. I mean, because we don't know what this thing looks like, right? Can you place these guys?
I don't think so. It's probably going to be one degenerate set.
If you do this, there's going to be something degenerate, something crazy going on.
I mean, yeah, if it was really, really long and they were all really long, I could probably.
Well, if it's really long, then something might get contained within another, and that's not allowed.
Okay, but it might not.
So,
happen.
well, so show me. So, which one do you want to make long? A,
Okay,
right?
So
You would have to make, forget about that picture. Oh, this is your graph. This is what I see. And yeah, well, none of the others are going to be connected. So what's it going to look like now?
I mean, that actually,
Works?
that worked, that one right up there on the board. Isn't that exactly what happened?
No, but you had A intersect C intersect D here.
Oh,
Since they're all single intersections, that means they're all within A, and no other one overlaps with another one from A.
All right, so if you want, I can also
Yeah,
put,
right, in that case, yes.
I can also put A intersect C intersect D. That's fine if you want. Okay, then what?
I didn't see that part right. Then in that case, maybe C will be contained in A, and then
Yeah.
A will still intersect with D. Yeah.
Exactly.
Okay. Yeah. I didn't see that.
Right? So you have to kind of play with a few things in your head. I won't have time to prove this rigorously for you, but essentially you cannot have a vertex that's adjacent to 3 other guys. Or what if I have A intersect B here? It would, of course, be adjacent to A or to B. Can it also be adjacent to A intersect B intersect C? Is this possible? Here I've added one, here I've subtracted one, right? Can this be part of my graph? Is this even possible? Can I have a region that has only a region with only B, a region with A intersect B, and then a region with A intersect B intersect C? Is this possible?
No.
It's not possible, right? You can see this. I mean, if you kind of think about this and try and place these guys, you see that there is a problem. It doesn't work out. What this is telling you is that when you build that graph, you're not going to have vertices with more than 2 neighbors. Okay? If there are no vertices with more than 2 neighbors, it all becomes just either paths or cycles, but we can prove that no cycles are possible here. Okay? So therefore, it must just be a path. If it's just a path, I'm just going to straighten it out and I have my order. Is this clear? So roughly that's the idea. The annoying part are things like this, where something ends and something starts immediately. If that happens, then you might have to jump. So for instance, actually even that is an easier case. If I have yet another, if I have something like this, if I have E going from here to here, if I have F going from here to here, and if I have G going from here to here, then it causes a fairly horrible problem, because now I'm going to have only E, right? Let's see. Let me use a different color. I'm going to have only E. I'm going to have E intersect G, then F intersect G, and then G. Sorry, F. Now when I draw the graph, what happens? There'll be an edge from here to here. There'll be an edge from here to here. But then these two won't connect. And that's going to cause you a problem, because now G is not together. Right? So when you have disconnected pieces and you have things in 2 different pieces, then you can connect them. So we have to do that separately.
We can't connect the G with the G?
You can. If you did that, then it causes trouble elsewhere. So you have to be careful. I'll tell you where it causes trouble. So if you're going to connect these 2 guys, then you have both a deletion and subtraction and an addition. Then your A intersect B will become adjacent to A intersect C. And you're not going to put them next to each other, at least not in this case. So what are you going to do? So it causes trouble, and you're better off dealing with it separately. At least that's what I think. So what did you learn? What's the algorithm? The simple case. Tell me the algorithm for the simple case.
To build a graph based on the differences of the set.
So you take the regions, make them vertices, then
add the edges.
based on.
If you subtracted a set or included a set.
Right. So if the difference is just one set, you join them by an edge, and then.
And then the graph you end up having is creating the path and you get the order.
That's right. Well, if you ever see a vertex with more than 2 neighbors, you can simply give up and say this is never going to work out.
Because there's a degenerate set.
Right. Yeah.
So for that case where it's E then F,
Yeah.
differ by more than just 1,
Yeah.
can we treat it as, so in this case it's as components, right?
Yeah, you can
graph.
put E anywhere you like and F anywhere
Yeah.
you like, yeah.
But so, then we can either do E and then F or F and then E.
Yeah,
Doesn't
they're
really
all
matter
going to be correct
because it's
answers.
just different graphs.
Yeah.
But for cases like that, can we still build out one component as E and then E goes to EG? And then when we're trying to go to the next component, can we see if that next component
Yes.
starts with either E or G?
Well, then you have to see that in this component there's a G, in this component there's a G, and then you have to link them together.
Yeah.
So yeah, that's what I'm saying. You have to do some extra surgery to this in order to get the right answer, because here there's only one answer,
Yeah. Yeah.
right? So you have to treat that as a special case, but it's possible to do that separately. So first you deal with this nice case where everything differs by only one set, and then you check whether there are these, so remember they're all going to be disconnected components. You check whether the components have something in common.
Yeah.
If they are, then you have to make sure. So sometimes you may have to flip something, okay? So for instance, over here, you may have put E intersect G on the left of E. And so maybe you have to flip something in order to make things right. So there's a little bit of extra work there that I haven't quite gotten into, but I wanted you to understand the basic idea, right? The basic idea is that these regions form what are called as cliques, and these cliques can be put along a straight line. Okay? And essentially it's a graph problem, even though it looks nothing like a graph problem. And the graph has some very, very nice properties. So if you think of these guys as your vertices, and say that, oh, these two intersect, and so therefore I'm going to put an edge, then what happens is that each of these regions corresponds to a clique, meaning there are several things that are connected to each other. Over here, for instance, you have A, C, and D, all three intersecting, and so you're getting a triangle. So if you think of these as cliques, then essentially you can order the cliques in such a way that they have a linear ordering. So these are called interval graph problems, and so there's a whole lot of theory behind this, but most of this is intuitive. Most of this you can kind of figure out by kind of staring at it. Yeah. Make sense? I think I'm way past time, right? I should stop here. Yeah, let me stop here. Thank you, guys.
Thank you, Professor.